My name is Kathryn Chapman, and I am presenting our submission for the Cantemist 2020 Shared Task Track 3. The name of our paper is Automatic ICD Code Classification with Label Description Attention Mechanism. ICD codes classification is part of extreme multi-label classification, which suffers from something called the tail end problem. This essentially means that the vast majority of the labels in a label space occur with very few positive training instances. In this data set in particular, there are 850 unique codes across all data splits, and over half of these occur with only one document. So this is a very imbalanced data set. Predicting these high resource codes is relatively easy, and doing so tends to achieve pretty high scores across various metrics, but the real challenge is capturing these low resource codes. In order to capture some of these low resource labels, we decided to make use of external data, namely the textual descriptions which accompany each ICD code. These describe the diagnosis that the code itself represents. Next, our baseline model is just a simple BERT encoder, which takes an input document and outputs this CLS vector, which represents the entire document, which we then pass to a classification layer, which gives us Y, our vector that we use to make our model's predictions. For our main submission, we developed what we call this label description attention mechanism. The first step is to encode all label descriptions and a batch of input documents at the same time in a BERT encoder, which is updated during training, and then taking the sequence level or word level output, thereby giving us word level representations for all of the words in the input documents and also all of the words in the label descriptions. Next, we multiply the word representations from the input documents with those from the label descriptions, which ends up giving us a bunch of dot product attention scores between all of the words in all of the input documents and all of the words in all of the label descriptions. Next, we take these attention scores and pass them to our first learn parameter, which essentially just collapses along the word level for the input documents. We reshape this, pass it to another learn parameter, which does the same thing except for the label descriptions, and finally we have Y, which we apply sigmoid to, and then we make our model's predictions. As BERT has a maximum sequence length of 512, we had to deal with long documents by fitting them into a single batch using the sliding window approach, and then taking max pooling over the Y batch dimension. To deal with code ordering, as we were required to submit our model's predictions in ranked order, we simply ordered them by descending order of the confidences associated with those predictions. Additionally, we developed a custom loss function, which we call a balanced binary cross-entropy loss function, and this essentially just calculates positive class weights based on the positive to negative ratio per example in a batch, and this substantially increased our model's recall. And now finally, we will discuss our results. The table here shows our final submission along with some additional post-submission experiments, and we will discuss this in a moment, but first I would like to point out that in the test set, there were 386 unique codes. 256 of these were seen during training, and 130 of them were unseen. Additionally, across all data splits, there were on average 5.4 codes per document. Now, looking at the table, the metrics alone say that number 2 is the best, as it receives a mean average precision of 48.2. In fact, even the baseline, number 3, performs better according to mean average precision than what we submitted as our final model. Rather than choosing our final model based on mean average precision alone, we decided to explore the types of predictions that our models were making, and we found some interesting things. So the baseline, for example, we see predicts 52 unique codes, which isn't a whole lot, but even worse, it assigns those same 52 codes to every single input document, despite the fact that it still achieves an okay mean average precision. Number 2, this label attention model, it's a little bit better. It assigns 76 unique codes, but 93% of those on average are assigned to the input documents, which is 14 times higher than the actual average. This, therefore, is what motivated our decision to choose the final model that we did, because this one predicted 178 unique codes, meaning that it captured more of those lower resource codes, while only assigning on average 15 codes per every document. Therefore, our decision to submit this final model was motivated by the fact that this one didn't seem to just be tricking the metrics by over-assigning codes, or by assigning the same exact codes to every single document. That concludes the presentation, and thank you for your time.